Welcome to How Low Can You Go? Now, how do we know we're amongst geeks over here? Well, first of all, Jack Shirazi from the Java Performance Tuning newsletter is in the house. Secondly, it's Halloween, and you're all here listening to a Java talk. I mean, haven't we got anything more exciting to do than that? Well, hopefully, in terms of trick or treat, it's a treat for me to be able to be here presenting to you. And we might be able to learn a few tricks about low latency programming. Before I start, I'd like to thank the LJC for organizing the event. And in particular, I'd like to thank Dominique, who I corresponded with. I looked recently, there were 51 emails, no less than 51 emails to get this event organized. Unlike the low latency messages, these messages, each one needed a considerable amount of attention. So thank you to Dominique as well. So what is this talk about? First of all, it's about ultra low latency programming. Now, what is ultra low latency program? I'm going to define it as sort of in the area where we're having response times of less than 100 micros, and also, and most importantly, where you care even about your outliers. So you care about 1 in 10,000. That's the 4 nines. And the way we're going to look at this, we're going to look at it through the lens of 3 questions. The first question is Java an appropriate choice for a low latency system? Then we're going to have a look at what specific development techniques do we have to employ when it comes to low latency systems? And thirdly, do microservices have anything to offer low latency systems? Okay, I want to start with a story about the low latency industry. This might be familiar to you if you've read the book Flash Boys. So in June 2010, Spread Networks laid a straight direct cable between Chicago and New York, right? No mean feat. It was 827 miles long. It cost $300 million to lay. And if you want to use it, it will cost you $150,000 a month. Now, why go to all that trouble? And the answer is because it's 3 milliseconds, that's 3,000ths of a second faster than the competition. Okay? Now, just remember, a GC pause can easily last over 3 milliseconds. So imagine someone from your organization has just shelled out $150,000 a month, and you've got latency spikes of 3 milliseconds, completely negating that. Secondly, another anecdote. I was working for a market-making company, and we had a bug in our system. Every so often, there was a latency spike. Now, how did we know about that? We were sitting on the trading floor, as often you do when you're a low latency developer, and every time there was a spike, this happened, right? There was a trader, and he started yelling. Why did he start yelling? Because we'd been arbitraged to the tune of thousands of dollars, and this happened regularly. It took me 2 months to get to the bottom of why this was happening, and that's a whole different story. It was quite interesting. But the moral of the story is latency can cost you money. In finance, low latency is a huge business, and it goes all across the board. So in hardware, you can buy overclock boxes, they're fast network switches, acceleration cards, they're measurement devices, they're timing synchronization devices. It's massive. And then there's colo. So if you want to write really fast code, one of the benefits you get is being as close to the exchange as possible. Now, in order to get that benefit, you have to pay a large amount to the exchange to get space next to their servers. Also, software. Developing and buying specialist software is expensive. And you have to pay developers a premium for low latency experience, very important for all of us. Now, why should I get into low latency? I was the sort of child, whenever there was an electronic gadget or anything like that, I would start taking it apart. I wanted to know how it worked. And one of the recurring themes of this talk is there's an awfully long way between when you write a line of code and it getting executed by the hardware on your machine. And you have to open it up. You have to know how it works. And the more you know about that process, the better the low latency programmer you will become. And I enjoy that sort of thing. And that's one of the reasons I quite enjoy this area of technology. Secondly, you get to play with all the new toys. You're not stuck on an old version of Java and an old version of J2EE on an old server. You tend to get the new toys first because you're the one who can make the most difference. And thirdly, if none of those tick your boxes, well, you've got the possibility of a highly paid job at the very least. Okay, and end of my preamble. How many of you were programming Java 1.0? 1.0, 3, 4 of you? So you remember the days when Java was a noddy little language to write applets. And I find it remarkable that we've gone from the days of applet writing to where we are now, where people consider it a good choice for a low latency system. There's a bit more about me. I've been working with Java, therefore, for 20 years, and in real-time and HFT system 10 years, done a variety of different applications. My career, I've been through software development, startups, bigger companies. I work for open source for Chronicle. You should all check out Chronicle software if you're in the low latency space. And now I work as a low latency Java consultant to investment banks. So before we get on to the first question, I don't want to take anything for granted with what people know or don't know. So just an introduction with timescales. A millisecond is 1,000th of a second. A microsecond is 1,000,000th of a second. A billionth of a second is a nanosecond. Now, what about the speed of light? Light travels roughly 1 foot per nanosecond, and that's in a vacuum. If you're going through a fiber optic cable, which we always are, it's about 2/3 of that. So if you want to go from London to New York, it's going to take you tens of milliseconds. Now, you might think, well, a nanosecond, that's not very much time. But let's consider this. If you've got a CPU running at 4 gigahertz, you're performing roughly 4 cycles. You can do 4 instructions per nanosecond. If you have parallelism pipelining in the CPU, and with parallelism, you can get roughly around 100 CPU clock cycles of compute power the time light has traveled a foot. Now, if you've got lots of feet between you and where you want your message to go to, the speed of light actually does start to matter. Now, we might think we're very clever here. You know, we're talking in nanoseconds. We really are the bee's knees when it comes to low latency. Well, the physicists just laugh at us. In neutrino physics, they measure in units called nanobarns, which are 10 to the minus 33, which really puts us to shame. Nevertheless, let's start with the first question. Question number 1. Is Java a good choice for low latency programming? Anyone recognize this? Premature optimization is the root of all evil. One of the most said sayings in our industry. Anyone heard this before? Yeah, most of you. Anyone know who said this? Who's this attributed to? Anyone? Knuth, yes, of course. It's Knuth. And where did he say it? He said it in a paper called Structured Programming with Go-To Statements. Came out in 1974. So this is nothing new. And the idea behind this is, don't worry too much about how fast your code runs. First, get it functionally correct. Does anyone agree with this? Anyone? Put your hand up if you do. Yeah? Most people agree with this. Right. Let's just look at what he actually said, because you take things out of context, that light little snippet, but what he actually said was we should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up on our opportunities in that critical 3%. And actually, in my experience, what happens is, in most systems, you want to tune the latency critical path of your software. And that can be just a small part of your system. So that's his 3%. Anyway, let's go back to the question. Should we build and then optimize? Or should we optimize? Should we build with the optimization at our forefront? And that's a really important question. And we have to know the answer to this. So let me digress before I answer that question. Now, this is a really fast bike. I'm a bit of an amateur cyclist, and that's the sort of bike I'd like to own one day. Now, actually, I have a reasonably good bike, and I could customize it. I could get carbon fiber aerodynamic wheels like the one in the picture. I could get an electronic gear set, a better hub, more aerodynamic clothing. And maybe, if all those worked out really well, I could add an average 5 kilometers an hour to my ride. Now, I'm not very fit, but if I was a Tour de France rider, maybe they could bring their average up from 30 kilometers an hour to 40 kilometers an hour. But let's say we wanted to average 100 kilometers an hour. It wouldn't help what sort of bike we would need, or how much we could customize it, or how fit we could get. For that, we'd need a car. And it's exactly the same thing for programming languages and frameworks. You need to understand, before you start, what is possible within your domain. So I'm going to look at a very simple system here. This is a DMA application, direct market access. Your client sends you everything in the box is our application. It's made up of 3 separate processes. The client sends in messages. We have a fixed parser that parses these messages, maybe does some sort of validation. It turns it into an object. We pass that on to an OMS, that's an order management system. That does some risk checks, it consumes market data, and if everything's okay, it passes it on to another process which has a fix engine in it. That parses it again, turns it into a fix message, and sends it off to an exchange. So what I'm measuring is time from here, when the packet hits that edge of our system, to when the packet leaves the system. Let's look at how fast we can go in different languages. So now these are ballpark figures. I don't want to start any flame wars. You might have done this sort of thing, but these are ballpark figures. For Java, if you're really, really good and you have really good hardware, you can aim for around about 10 microseconds. And that's your fastest, those will be your fastest response times. But that sort of ballpark, you can sort of aim for that. Now, if I was using C and C++, I'd probably also be looking in that same ballpark, right? If I was using an FPGA for the same system, I could go down by an order of magnitude and be looking around about the single microsecond mark. And if I was really, really quick and I used an ASIC, and we'll talk about this, you can go for about 400 nanoseconds. There are people who claim even faster, but those are the sort of ballpark figures. And if you want to use Python, well, just forget about it. You know, you're not at the races, I'm afraid. Now, there are particular challenges using Java. Java is not the cure to everything. And let's just have a look at them. So let's start with the elephant in the room. The elephant in the room is garbage collection. And it's a managed language, so it runs within a container, a JVM. And every so often, we're going to have to do garbage collection. The world comes to a stop, and we can pause for an arbitrary amount of time. We're going to have to address that. There's the warm-up. Java is rubbish at the beginning when you start it up. So the first 10,000 iterations, just write them off. So you need to have a way of priming your system in such a way that doesn't take down your bank or hedge fund by sending horrible orders to the market. You have to be careful what you're doing, but you do have to do it. Thirdly, there's unpredictable compilation. Sometimes, and I've found this in my experience, that you see, for whatever reason, Java tends to decompile bits of your code, recompile them. Maybe there's a branch prediction that went wrong, something like that. It can be unpredictable and cause small amounts of latency. And here's a really big one. You don't have control over the memory layout. You can't do the same thing as you could do with a C struct. You can in C#, but you can't in Java. They have been talking about putting this value types in the language, I don't know, for years and years and years, and I'm still hoping for them to come in very soon. And if you want to start playing with the low-level concepts, there's a slightly unnatural way of programming it. You use unsafe, and unsafe is not meant to be safe. And finally, there's certain CPU instructions that are just not available to you in Java. What about C++? Well, there's a reason, a really good reason, why Java has replaced C++ as the most using programming language in finance. And the reason is, it's because it's way more productive and just easier, and there are more developers, and the whole environment is richer now than C++. And you want to spend your time developing, not pointer chasing. So that's why C++ may not be your first choice, even though it doesn't suffer from a lot of the problems we saw on the previous slide. And if you want to be really, really fast, you don't use C++ anyway. You would use FPGA. FPGA is now the up-and-coming technology. It really is becoming ubiquitous amongst banks. And I've just been told that even you can get FPGAs even on Amazon, on their cloud services. So the space between the utility of Java and the speed of FPGA is constantly contracting, and C++, to a certain extent, although there will always be a place for it, it is being squeezed out slowly but surely. How about programming in hardware? Just spend a brief moment talking about that. So an FPGA, for those who don't know, it's a field programmable gate array. So it's a chip that you can basically program. It's not as fast as an ASIC, which is an application-specific integrated circuit, which is a one-off production. Now, the problem with these are, although they're very fast, it's still difficult to program in them. So an FPGA, a typical compile, will take about 8 hours. It's slow to market. One of the things you want to have with your ultra-low latency system is you want to make a change in your code and you want to deploy it pretty much as soon as possible. You don't want to wait hours and hours for you to be able to do that. As I said, they're very expensive. And it's interesting. I found this graph of when do you produce an ASIC? This is like for people producing washing machines and stuff. It's when you go over about 400,000 units, it's worth doing an ASIC rather than an FPGA. So it's worth running your own run of your specific chip rather than doing a programmable one. Now, we're talking about a run of maybe 1 or 2. So imagine the price of writing your own ASIC. I don't doubt there are certain hedge funds that have their own ASICs. I've never come across it, but the speed with which some people are reacting in the market today is pretty fast. Anyway, we're not really talking about that. I want to talk about the Aeron story, and this is something I heard from Martin Thompson. He's that guy over there. These are three really clever chaps who developed a new ultra-fast, low-latency messaging system. So originally they wrote it in Java, and then they ported exactly the same algorithms to C++, C#, and Go. And which one do you think was fastest, given they're very good developers? And they ported the same algorithm. Someone want to guess? Well, of course the Java one was the fastest, yeah. The Java one was the fastest at first. But then they did a round of optimizations. They spent some time, and here's the real shocker. Which one came out faster after the first round? Well, what do you say? Huh? Go? You think Go? No, it wasn't Go. It wasn't C++. It was C#. And the reason C# gets the nod over Java was because you can optimize the memory layout. Now, Martin is convinced that if they spent more time and effort doing optimizations, that C++ would be the fastest, and that sort of makes sense. However, the question is, where should you spend your time? How much time do you want to spend getting more and more out of your language as opposed to improving the rest of your code, the reliability, the measurements, the testing, the algorithms? Okay, but it just shows where Java is. Now, this slide will be familiar to Jack Shirazi, who's sitting with us. It's taken from one of his newsletters, the Java Performance Tuning newsletter, which you should all sign up for. And we categorize Java programs into 4 categories by their target latency. One is seconds, hundreds of milliseconds, tens of milliseconds, and under a millisecond. And you have to have these different types of approach when you're aiming for those different types of low latency targets. What I'm going to say is I'm only looking at number D, under a millisecond. I'm not sure about all of these because I have tried. Some have better effects than others. But the really big one is you are not allowed any GC. So that's if there was one thing you take away from that, it's over there. And so how should you not, just a couple of slides talking about not creating garbage. So you don't want to force people to have to allocate. And one of the ways you can do that is by creating really good APIs. So I'm going to highlight a few good APIs. This is from Chronicle Map. For those of you who don't know, Chronicle Map is a memory mapped sort of map where it allows you to write to the map interface but store the data in a memory mapped file so it can be shared amongst different JVMs. And normally you'd use the get method in a map. The problem with the get method is because the object is being serialized from off-heap memory, you'd have to create a new object every single time you call get. So what they've given you is this get using function. And the get using takes in this name, which in this case is a string builder. And what it does is it hydrates that string builder. So you just keep repopulating, or you've got the option to keep repopulating the same object. So you're not doing any allocation. And you should always consider that when you're writing your code as well. And here's something else. Strings are probably the biggest cause of allocation within Java. And you do have an option. You don't have to create strings. And string implements something called char sequence. So often you can work with char sequences instead of strings. So over here, for example, let's say you're reading off a file or reading off a stream, a TCP stream. You can take your byte buffer, you just find the beginning of your word, your string, and the length, and you call a set. At no point have we created a string. Only if you call toString do you create a string, and you wouldn't call toString. And you just use this instead of the string. And what you can do here is, let's say you've got an interface. Say I've got a piece of text, and I want to count all the unique words in that piece of text. So I've got a method here called countUniqueWord. And instead of passing in the string word, forcing the person who uses my API to create a string, I'm going to use char sequence instead. What am I going to do with char sequence? Well, there's a very, very nice library from a guy called Roman Leventov. He's someone I worked with at Chronicle. It's called Kolobok. And Kolobok has produced its own maps. And one of its maps is called here, it comes from the hash obj long maps. And it creates an obj long map for you. And what you can do with this map is you can actually call with key equivalence, which means that when I want to look up a word, if I want to see if my map contains my word, I can use the char sequence, and it'll use the equals method on the char sequence rather than the string. Now, if I'm going to have to put in, for the first time I put something into that map, unfortunately, I'm going to have to create the string because I need the string in the map. But subsequently to that, so 99% of the time, I just go into this piece of the code, and I just use add value if I had the word. Again, no string creation. And have a look at Kolobok if you want to get into this. And so the summary to question one is, Java is a reasonable choice for a programming language, for a low latency system, if we're looking at greater than about 10 microseconds. Now, if you're looking below that, don't even start with Java, would be my recommendation, because it will be really, really difficult to get there. Okay, question number 2. How should we approach software development when it comes to low latency systems? Again, let's digress. Okay, there was a podcast, I don't know if any of you heard it. I can't remember the name of it now. They got famous Java personalities to come and talk about what they were doing. And as an icebreaker, they always ask, is computer science a science? So I'm going to ask this now. Is computer science a science? Those who say yes, put your hand up. That's most of you. Those who say no, put your hands up. Okay, most of you think it's a science. Well, it's one of these semantic arguments, isn't it? Let's define what a science is, and then we can know what we're talking about. So, what is a science? A science seeks to explain phenomena through theory, hypothesis, and experiment in an effort to ascertain natural laws. So that's what most of you think you're doing all day long, really. Okay. Now, I would say we're more in the engineering field, and that's why even though we're called computer scientists, we're also called software engineers, aren't we? Engineering builds one level above that, and it seeks to apply natural laws to the solution of practical problems, probably more what we're doing every day. Now, I would say, and here's my argument, that when it comes to low latency programming, it is a science. And that's because you have to use the skills of hypothesizing, measuring, and then explaining what you're doing. So low latency requires a scientific approach, and these are the steps you need. You have to come up with a hypothesis. So you think, my code is going to run faster because I'm going to do this. I have no idea whether that's the case or not. I don't know. I can't test it in JUnit. I have to build a very elaborate experiment, probably. You know, I have to test my whole system. I can't just look at one piece of code in isolation with a JMH benchmark or something if I really want to measure it properly. And then I can draw conclusions. So why is that? And this is something I mentioned earlier. And the reason is because our code is a very long way from what we write in Eclipse or in IntelliJ till when it actually gets run on the hardware. It's very hard to reason about that. And I'll tell you something that happened to me. I was working on a system in a bank, and I thought, look, here's a perfect opportunity for an optimization. A really good way to make a name for myself, right? I did make a name for myself in the end, but for not for good reasons because of this. And I said, there's this calculation, quite an expensive computation, which was being done in a tight loop over and over and over again. I said, why don't we just cache these values, right? So I spent some time, wrote an efficient data algorithm, a data structure to store all the cached values, and then we ran it. And it turned out it was 3 times slower when I actually ran it using the cached value than when it actually computed it each time. And the reason for that is I'd made the classic mistake, which is not understanding that on a CPU, and you can practically say that operations on the CPU are almost free when compared with the memory access. So the memory access takes orders of magnitude longer. So even if you have a relatively expensive computation, sometimes it's faster to run that than to go and fetch in data, especially if it's in the level 3 cache, or even worse if it's in main memory, into your CPU. So that's why I say we need a scientific approach when it comes to low latency programming. Now, just quickly, what is a real-time system anyway? And here's some ways you can describe a real-time system. It could be your speed, it could be a function of your throughput, maybe your mean latencies, or your slowest latency, or being predictable with your latency, or even a function of your reliability. And these are the general classifications for real-time system. There's a hard real-time. Hard real-time means when your slowest response is what really, really matters. That is the be-all and end-all. So if you've got a weapons system or a pacemaker, you do not want your slowest response ever to exceed a certain threshold, or you could have terrible consequences. Then the exact opposite to that is first to the bell. And that would be, let's say, a cycling team, where you don't really care which cyclist wins from the point of view of the team. You just want one of your cyclists to win. Even if some of your cyclists are really slow or even drop out completely, as long as one of your cyclists is the fastest, that's okay. Then you have web real time, which means as long as the user doesn't notice, well, it's still real time, the user doesn't notice how fast it is. They may not notice certain spikes, they may notice others. And then we get to what most low latency systems are, which is soft real time. We do care about all the latencies, we do care about them, but if there's one particularly slow latency, it's not going to kill us, and we don't really want to sacrifice our mean latency too much for the very, very furthest outliers. Okay, and a typical low latency graph, for those of you, anyone familiar with that sort of curve? Anyone seen that while they're measuring low latency? Well, anyone working in low latency should have seen this. They always look like this. They always have this sort of hockey stick where it sort of looks pretty nice up until the 99th, and then it goes sort of shooting off the end. And this is something I measured when I was doing Chronicle Fix. And we always measure this way because we care about the outliers. And the problem is, as you go up the latency graph, it gets harder and harder to diagnose and fix the issues because it might only happen 1 in 10,000 runs. How on earth are you going to fix something that you only see 1 in 10,000 times? It's really hard, and it requires sort of specialist tools, specialist experience to be able to do that. Now, coordinated omission is something really important. Normally, how many people have done this? When you have a system, you want to time it, what do? Well, the first thing I do in my system, in my start method, is I go long start equals system.nanotime. So that's my start time, wait till the end. Then I get time equals system.nanotime minus start. That's how long it took. But you might have a system that looks like it's running really well. In fact, what you've got is an overcrowded train station. So what do I mean by that? When you take a train somewhere, you time latency by the time that the train was supposed to have left, note, supposed to have left, till the time you arrived. Not from the time your train left. And that's the danger of doing that start the way I described it at the beginning. You have to be really careful to measure from the time that the operation should have started. And too many of our systems, too many of our test harnesses don't do that. This is exactly what happens. You have one spike. That one spike, what it does is it causes a knock-on effect. That's what this line is. It can cause it for hundreds and hundreds of further measurements until we reach normal again. That's what you have in a train station. If you ever use Thameslink, I don't know how many have used Thameslink over the past year, you'll feel like you're somewhere along that line over there. And what effect does it have on your percentiles? This is something taken from Gil Tene. He works for Azul Systems. And this is what it looks like uncorrected. It looks like your percentiles are doing rather well, but no, they're not. They're over there. So always remember to measure using coordinated omission. Now, one thing you should always do is document your latency requirements. And I've been in many a dispute between software vendors and clients about what did we mean when we said low latency? So this is the very worst type of requirement. The messages should take 100 microseconds. Okay, really? What does that mean? So a real-time contract looks at, you have to have at least these components. Activity A. Now be really, really specific about what you're measuring. When it runs as part of a system S. So is it going to run standalone, or you're going to run within a bigger system? And if it runs within a bigger system, that's going to have an effect on you. For a throughput of a certain amount of events per second, always consider your throughput. Your throughput, having a higher throughput, by the way, doesn't always slow you down. Sometimes it can speed you up because it keeps your software hot. For a duration of time T, how long are we going to run the test for? Are we going to have bursts within the test? On hardware H, define exactly what hardware. If you have an overclocked box, I was just using the other day, 4.8 gigahertz overclock box, you get dramatically different results from when you're running it on a 2.5 gigahertz machine. And how is your operating system going to be configured? Are you going to have admin rights to change critical things? Are you going to have network acceleration? Are you going to have SolarFlare or Mellanox cards in there? And then your latency shouldn't exceed a certain latency at a certain percentile. That's really important. And you have to go all the way through the percentiles and also make sure, are you going to be correcting for coordinated omission or not? And how are you going to time it? Are you going to use, let's say, a Corville device, so you're going to packet capture, or are you going to rely on some sort of printouts or HDR histogram or something like that? And this is an example of something we did when we were at Chronicle Fix. And you can see we were very specific about the throughput, the duration, the type of box we were running on, and we went all the way down to the percentiles, even up to the worst. Now, I would recommend never, ever put in the worst, because it's, as I say, it's really, really hard to get your worst one down, but that was in there. So, for ultra-low latency development, you will need, now, I don't know if when my kids were young, they used to have these comics, and in the comic, there was always this thing you could make using sticky back plastic and washing up liquid bottles. And before you started making it, they always told you exactly what you would need to be able to make this model, to make sure there would be no disappointment at the end if you were missing one of the parts. So what do we need? So if you want to be in the sub, say, 20 microseconds at the 3 nines, well, what will you need? First of all, you need one powerful server with admin rights to run the application. Yeah? The second is you need another server to drive the test harness. It's always much better if you can replicate what's going to happen in the real world. Okay? You're going to need a very fast switch or a cross-connect between the boxes. You're going to need packet capture of some description. So how are you going to measure the traffic in and out? Ideally, you want to measure it right at the edge. So this helps with coordinated omission. And before it gets even through the TCP layer, a standard industry mechanism nowadays is using a Corville device, but you could use Wireshark if you capture your packets. You're going to have a test harness, a really good test harness that produces your percentile data and graphs. And ideally, you want to automate this. So you're not going to have to manually run this every time. You can just click a button, and the whole thing will run. And here's some tips on measuring. Always measure, like we've said, from edge to edge. And also decouple your test application from the test harness from the actual application. You don't want a feedback loop. So you don't want to say, I'm only going to send in the next request when the last one's completed. You want to say, I'm going to keep sending them in at a regular rate, whatever latencies are experienced by the application. You need to be able to view the percentile data, so have some nice graphs and especially tracking it over time. And as well as your percentile data, you want to view your time graph data. And this is critically important. Let's say you see a spike at your 99th percentile. You say, oh, there's this rather large spike. Now, it could be that all those points of latency are at the very, very beginning of your run. And what does that tell you? That tells you haven't warmed up properly. However, if they're at regular intervals, well, maybe you haven't optimized for Nagel's algorithm or something like that, if they're very regular. If they're sort of clumped, well, that could be something else. So being able to view your latency across time is also something I've found very, very important. Now, have any of you read The 7 Habits of Highly Effective People? Yeah, you've read it? Yeah, you're always the same people who've done. So one of the things he talks about is only work in your circle of influence. And this is so important when it comes to low latency. So work out what you can possibly be responsible for. So we never build on hardware. We're always building at least on the operating system and usually on top of a framework. So benchmark your minimum application using your framework. So if you're, let's say, using Apache Spark or Splunk or Splink or whatever else that Apache offers nowadays, just write a null implementation and see how long it takes. Look at your latency in that null application. And let's say on the 3 nines, it's 500 microseconds. Well, that means you will never, ever be able to go below that. right? So sometimes I see people, and what they're doing is they build their whole application. They see, oh, it's 500 micros and then 3 nines. Let's see, and they start optimizing and optimizing. And what they realize, it's nothing to do with their application. It's what they're running on. So always work out what you are responsible for. Secondly, if you're responsible for the framework, well, then measure your operating system. Because if your operating system is not properly tuned, if that's got latency spikes, you're not going to be able to go faster than those. So the summary in question 2 is, be scientific when developing low latency code. Now, third question, microservices for low latency programming. And this is something I'm sort of quite into at the moment. You know, the term low latency microservices, is it an anathema or is it the way forward? And when I say an anathema, that's what I thought when I first approached this. And surely low latency microservices break up and introduce complexity into our process. So something which used to be in one JVM is now in 3 JVMs. Can that possibly work as fast? However, the idea of messaging and low latency microservices, it predates computing. It's in fact incredibly ancient. And here's a system, an ancient system. You might recognize this, right? This is our brain. Our brain is a low latency microservice event-driven system. Unfortunately, the latencies are pretty high compared to, you know, we're measuring in milliseconds compared to what we have in our low latency systems where we measure in microseconds. I think those are milliseconds there. But that's interesting. So I think actually, and I know because I've built some, that you can build low latency microservices and they can be really, really efficient. But what do you need? What are the features? The first thing is you need fast transport between the microservices. If you're doing TCP calls between your microservices, just forget it, okay? You're going to have to use shared memory. How fast is shared memory? Well, let's look at a couple of the open source projects out there. If you look at Chronicle Q, in an echo test, sending a byte from microservice A to microservice B, it being acknowledged and sent back, so it's the full round trip, you can accomplish that in half a microsecond. If you use Aeron, you can do that in 250 nanoseconds, which means a single trip on Aeron is only 100 nanoseconds. Now, even if you're talking about sub 10 microseconds for your whole application, 100 nanoseconds is negligible. So the cost of sending messages between the microservices is pretty negligible if you do it correctly. Second of all, make them single-threaded. You know, you have this beauty of having different microservices. Make them single-threaded and get the benefit of having a CPU pinned to your microservice. Now, there's been an ongoing debate between large JVMs and small JVMs. When I started and Jack started programming in Java, we all wrote small JVMs. And the reason for that is because we didn't have 64-bit JVMs yet. So the maximum heap size was 2 gigabytes. We wrote lots of small ones. Then 64-bit came along and people went crazy. You know, there are JVMs out there with 128, 256 gigabytes of data, with about 2-hour garbage collection times in those, and 1 million threads. And we all have to be experts in threading, multi-threading, and your CV's full of, oh, look, I can do this with my... The answer is no, go back to your small JVM, use single-threaded microservices, and you can get masses of benefits. So firstly, there's no synchronization. So when I've done this, the word synchronize doesn't appear anywhere in my code. If I want to do object pooling, I don't have to have complicated strategies of, well, this thread's taking, this thread's putting back. All I have to do is use the single thread to put and take into my object pool. If I need to scale out, all I have to do is partition my data and add more microservices. Hog the CPU. Someone once described hogging the CPU as this, and it'll be familiar for those of you with children. It's like you're sitting in a car and your child asks, "Are we there yet?" And you say no, and they say, "Are we there yet?" No. "Are we there yet?" No. And we keep going until we say yes, and that doesn't stop them. But, you know, that's exactly what happens when we hog the CPU. That's what we have to do. When we're waiting for a call on our shared memory, someone writing to us, just spin, keep spinning, and make sure no one else has got that CPU. So block all the interrupts from that CPU. So that's important as well. Also, record all your inputs and outputs from your microservice. Make sure those are recorded in shared memory so that you're not paying a huge penalty, but record everything. And it's really important to have all your inputs and outputs recorded when you're talking about low latency, because you need to be able to replay what's going on in production, let's say in your test system. You need to try different things out. How are you going to do that? How are you going to find your 10,000th latent, 1 in 10,000th latency spike if you haven't recorded your inputs and outputs? So that's important. And map your microservices onto your hardware. You have to, again, know what your hardware destination's going to be. So you don't want to cross NUMA regions. Your microservices shouldn't cross NUMA regions. So if you have a NUMA region with 8 CPUs, work out which of your microservices are going to run on each one of your CPUs. You've really got to think about that when you design your microservices. And if you do all that, by the way, you have to do that even if you don't use microservices. But if you do all that, you can have really, really effective microservices. I just want to end, finally, with the hardest areas in low latency systems. And these are things you need to consider right from the beginning. The first is like wait-free data structures. You're going to have to do, I mean, do people know the difference between lock-free and wait-free? Anyone know the difference? So a lock-free data structure means that your thread can always proceed, right? Nothing from, there are going to be no sleeps in your system. So those are really important when you're doing low latency, because a single time that you schedule your thread to sleep, for whatever reason, it can take a long time to wake it up again. But wait-free means not only is it lock-free, but that you can finish your computation within a certain number of cycles, right? You know how long it's going to take. You're not just going to keep spinning and spinning. So you want to write data structures for that, and that's another talk in itself, how you do that. But those are those can be quite difficult to write. Fortunately, there's quite a lot of open source stuff available. Now, resilience and high availability going together with failover if you want hot systems. Now, what we don't want to do, we want to pass all our messages across shared memory, but we don't want any of our messages to get lost. So how are we going to deal with that? I mean, if we're waiting for each message to go from my machine to another machine, and then we check that it's actually been replicated using TCP or even UDP across to a different machine, it's going to take forever. So we need a strategy. We've got to work out with our client, with our business, how are we going to deal with resilience? One good way to deal with it is make your endpoints responsible for keeping state. But you do have to worry about those. And second of all, creating a good measurement and a good test harness can also be pretty difficult. Let's summarize. So we asked 3 questions, and these are the 3 answers. 1, Java is a reasonable choice, I think. 2, when it comes to low latency, be scientific. And 3, if microservices are adapted for low latency, they can be a very good pattern for low latency systems. Now, I want to take questions now. I think we have a little bit of time, or I'll take questions afterwards. If you want to contact me, probably the best way is on LinkedIn, look up Daniel Shaya. Thank you.